Okay, the first building block part that I wanted to cover is one of my favorites. It's the multiplexer. Okay, so let's get started with that. Number one in our four-step cadence for all these building block parts is the functionality. So the basic job of a multiplexer is to route a signal or to route data to a certain location. Okay, so for this example here, we have this shape distinctive schematic symbol. This is common for the multiplexer. It almost looks like a truncated arrow, and it shows the direction of the data movement. So in this example, we have D0 that we can route to Y, and we have D1 that we can route to Y. We can do this routing by the control line or the select line. So notice when I click here and I change S equal 1, now D1 is routed to Y, and when I go to 0, it is D0 that's routed to Y. Now, I'm showing this as essentially a scalar, a single Boolean variable, but we can make this a vectorized type of approach, and I show that next when we look at the hardware. Okay, so with the hardware, we are taking individual bits from the data line that would be D0. So D0 has the most significant bit, which is a 1, and the least significant bit, which is a 0. And we have essentially a stamped version of the multiplexer hardware for each bit. All right. So I like to think of D0 as the data line with 2 bits. This is what I would call a minimal representation of a multiplexer that captures all the features that you need to know. So the things you need to know is with a multiplexer, there's a select line. So when I select S equal 1, I get this lower AND gate enabled on both of the bits for the D10 bit and the D11 bit. Okay, this gate, I call it enabled because it's got a 1 coming to this input of the AND gate. So the output is just going to follow whatever D1 bit 0 would be. And then because this goes through the OR, something ORed with 0 is always that something. So this flows on through to the output and you get Y0 connected to D10. All right, so let's just talk about this for S equals 0. For S equals 0, we have, let's go down here to the most significant bit. For S equals 0, it's the upper AND gate in this template that's enabled. So the input to this AND is a 1. So 1 ANDed with D0, D0 flows to the output. So D0 ORed with 0 is D0. Okay, so D0 bit 1 goes to Y1. All right, I think it's pretty obvious how that works once you see it. Once you see this gating kind of function or this routing kind of function that an AND gate has. And the OR just passes things through with the idea that only one of these inputs is going to be is on. And so that lets it pass through to the output, and we can connect multiple paths through an OR gate. Okay, so that's the hardware implementation. I would hope that you'd be able to sketch that if I asked you to draw a 2-bit 2-to-1 multiplexer hardware implementation on an exam. This would be the answer. Okay, so next let's talk about applications. All right, lots of applications. You could take a bus of data and route different things to a certain line. Okay, so that's a popular application. You could have, later on when you do computer architecture, you might have an ALU that has different operands, and you need to route registers to those operands. That routing problem is solved with multiplexers. It turns out we're going to learn that you can even implement Boolean functions out of multiplexers. And then another application is you can do time division multiplexing. We're going to do that in one of our labs. And you can do that with multiplexers. These are just a few applications. There's really a lot of things that we use multiplexers for. Okay, so the next part of our cadence is I like you to have in mind the description of the functionality. So it's related to 1, but I want you to see it in Verilog. Okay, so for a 2-to-1 mux, all right, so I have a very simple example. It's a 2-to-1 mux. I can look at the inputs. These are scalars because there's no vector notation here. Scalar inputs, scalar output. This is an assignment statement, and we directly assign the output using this kind of cryptic command. All right, so this is a Verilog construct, and basically the idea is because you see this question mark, we are conditioning on S. So if S is equal to 1, we do the first thing, so it would be D1. If S is equal to 0, we do the second thing on the other side of the colon, so Y would be D0. All right, so that takes care of the functionality using this kind of cryptic command. All right, I also wanted to show you a use case that I think is actually even more instructive, and that's a 4-to-1 mux Verilog description. Okay, so in this particular case, because it's 4-to-1, the select line needs two select lines so I can get all the different 4 cases. And then I wanted to show that you can use multi-bit data vectors. Okay, so D0, D1, D2, and D3 are now 8-bit vectors, and that means the output has to match. So the output is an 8-bit vector. So the 7 down to 0, that's 8 positions. That's what tells you the size of this multiplexer. All right, we're going to put this into an always block. I'm not going to describe what an always block does. There'll be another section in the book. If you're kind of fuzzy on always blocks, you can look that up. We are using a case statement here, which I think is relatively obvious if you've done any kind of programming that uses a similar type of conditional assignment statement. All right, so here's how it works in Verilog. We are conditioning on the input select. So select is 2 bits. So I showed the Verilog literals for all the combinations. Okay, so the 2 means it's 2 bits, B means binary, and this just shows the binary combinations 0, 0, 0, 1, 1, 0, 1, 1. On 0, 0, we route to Y is equal to D0. On 0, 1, we route D1 to Y, and so forth and so on. So it's pretty easy to see how this module is constructed, and it obviously encapsulates the functionality of a multiplexer. Okay, so that's an overview of a multiplexer. We're going to use these quite a bit in this class. It'll become second nature to you, but that's your first introduction to this.